Bonsoir. Who's there? Who's there tonight? Let me know how my microphone sounds. I think I fixed the problem, but you can tell me for certain that you can hear me. You should also be able to view the captions at the bottom of the screen as I'm speaking. If you press the CC button, that should be possible. Bonsoir, Kenold. So let's just wait to see who comes in here. I'll give it a few minutes. Can you hear me fine? How is the sound? Background noise still. There should be a humming sound because the fan on the computer is running to keep it from burning up or crashing, to keep it cool. I did buy a new computer and hopefully that won't happen in the future, but unfortunately that computer has not arrived. Pierre, what stopped the noise? Or, okay, just answer the question, can you hear me clearly? That's the most important thing. Very good, Alex, thank you. So let's take some time and hear from you. First, about your access to resources. Does anybody have trouble still with accessing the Comunidad platform or accessing the videos? Please let me know. Good afternoon. So I asked the question, or I'll put it in the chat. I just want to know if anyone there has trouble accessing the resources either in the Comunidad platform or is anyone having problems with YouTube. I am resolved not to use Zoom unless I really have to, because I don't want to learn it's not that I don't want to learn Zoom. I'm worried that I won't have the same functionality. And things seem to work so well right now. So there's 9 students right now. I'm just going to wait a little longer. So that's one question. And the other question is about, yeah, about YouTube. Have you sorted out how to see the captions, how to translate them, and also how to see the timestamps? I think we could add more to the timestamps. So if students find that some areas of the video are interesting, you can make your own timestamp in the comments, and I can add it to the description, so it gets marked for you. So let me describe what I mean. I'm going to open a video. So here's a YouTube video, and on this video, I'll make it a little bit bigger. No, that didn't work. Anyway, on the video you see I've put below here, I've entered these timestamps. I put these timestamps in the description. And if you find parts of the video that you want me to timestamp, you can write it into the comments section. Just like this is I have an assistant who helps me, and he just prepared these comments here with the timestamp. So if you want, you can put your own comment, and then I can include it in the official description here. Okay? All right, so how many are we right now? So 13. Just a couple more. In the last video, the one that the part 3, and I really apologize for my internet connection. I don't know if it's the internet that the provider who thinks they can conduct maintenance on Sunday, but we were not warned. I did manage to put up most of the third video, but got cut off at the end. So I just wanted to mention the last point I wanted to make on that video. And that's where I want to start today. Okay, so what I did on the last video was discuss the 5 features of a distribution and show you a systematic approach to summarizing data. I went through the first four. So the first was one was shape, and the shape determines the rest. With shape, you can identify the center, then the spread, number 3, and number 4 was gaps and outliers. The 5th, is where I got cut off on my video, and that is peaks. The peaks are where you have the most frequent class, And in the first graph, that would be between 40 and 49. This was for Maris, if you remember. For Ruth, if you remember. And then for Maris, I conclude that there are no distinct peaks. Here is the graph for Maris. And yeah, it looks like there's a mountain of information here, but it isn't a lot. And this class is not distinguished from this class. So I don't see a distinct frequent class, and I say no distinct peaks. So that's how I conclude the 5-number summary. And then what we conclude So remember, this was the document called summary data. I offer here, I present you the conclusions, all the summary information. So what we did last several classes was discuss the 5 features: shape, center, and spread. Then I make the calculation. And then gaps and outliers, I make the calculations here for you. And single or multiple peaks in the comments that I make. In conclusion, this is how I conclude for the question, who is the better baseball player? I say Ruth's distribution reports a consistent record, having an average 44 home run hits, and I mentioned the spread, give or take 11 hits a season. Maris' distribution reveals that he has 25 home run hits a season, where 50% of the time he is hitting anywhere in the interquartile range of 15 to 33 home runs. As Ruth's average number of hits in a season is higher than the interquartile range, that's what I'm referring to, this range, we'll say Ruth is clearly the better baseball hitter. Okay? So this document has 5 data sets, and I go through the process here of summarizing those 5 data sets with the 5-number summary and concluding answer to the question. So we've done these together. I did present you the spending data graph. That's how we started. And we can look at the concluding remarks, the summary statistics, etc. And let's do that right now. So if people are wondering where we are, I'm in this document here, sample problems. And on page On page 7, I have the graph that we discussed, the spending data graph. That's the grocery shopping data. And then on page 14, I have the summary. So let me allow you to open that up, and then we can talk about this some more. Sorry, the 13 and 14. I'm gonna show page 14 just because that's where the graph is found. All right, everyone have that page? All right, so if you remember, we made this graph by rounding the data, and I mentioned that we can smooth this out if you believe there's 3 groups, which I will make that assessment and conclusion that there are 3 distinct types of shoppers, possibly low income, middle income, and high income. But that depends on, we'll determine that better by investigation. Maybe these are consumers, maybe both groups are consumers, low and higher income consumers, and maybe this is a commercial consumer, like another business that's buying. So that would need to be determined. And as I mentioned, this is the split stem and leaf. This is going by intervals of 5. Let me write it by 5. If I was to draw the graph by 10, and this is something you can do when you're deciding what are the best size of class, what is the best size of class. If you were to go by 10, now my classes are going in groups of 10, 20, 30s, 40s, 50s, and 60s. When I smooth out, I only get 2. I get a strong peak in this class and a strong peak in this class. Now, you could propose that this is the drawing. This is the best representation of the regularity and the curiosities in the data set. If you believe that this is the case, so for instance, so you could have households as consumers, and maybe restaurants are also purchasing larger or more expensive items. Okay, so if that's the case, maybe you go with this sketch instead. But we stick with this one. In my conclusions, I go with the first one. Let's say I had some prior information, and I explain I demonstrate my calculations in the pages before. I show the shape is right skewed. The center I calculate, since it's right skewed, I calculate the median. Since it's right skewed, I calculate the 5-number summary. I calculate the interquartile range. Ooh, I didn't put it anywhere. So I should calculate the interquartile range. I do it below. This represents the middle 50%. That's really, my pen is sort of messy, isn't it? This is the middle 50% of data. What I'm going to do is make it bigger and then write. So the middle 50% is the range of values in the IQR, interquartile range. And when I calculate it, this is Q3, this is Q1, and these were calculated, remember, this is the maximum value. Sorry, that's not the maximum value, that's the minimum value. This is the maximum value. And this is the median. And I can calculate the interquartile range I'll go to the questions in a minute. And you can calculate the interquartile range 1945. All right? So that's the spread. Number 4 is the gaps and outliers, and I explain how to calculate those. And then the single or the multiple peaks. And in this case, the important thing to notice is that there's a peak here, here, and here. And those are the ones I mentioned. If you choose this drawing, the other drawing, you would have to mention this peak and that peak. Okay? So, what did we learn last week? You learned we met and I introduced you to the Unit 1 material here. I asked you to read through these notes, respond to the quizzes, get an idea of your strengths and weaknesses, accumulate a set of questions, and I proposed I would answer those questions. Then in the latter half of the weekend, I introduced this unit and I asked you to spend the week reviewing these videos. And now I turn it back to you with questions. Now I've been asked for a summary. For me to sit here and summarize what I just taught or to go over what's here in the video seems like inefficient and redundant. I'd rather mention to you, if you want a list of what you should know by the end of the week, so before today or today, you should, I will show you in the syllabus, according to the class syllabus, we have I've introduced this material. I've given you resources for Unit 1 and Unit 2. And the list of topics are here. So, if you want to ensure that you have full coverage of the material, make sure you understand all of this terminology here. Sorry, I just noticed my video isn't updating. I want to show you. Oh, I see. So this is the syllabus. And here you have all the topics. You should know all this. You should know all this terminology. You should know these by name. All right, so now what questions do you have? I sincerely don't see the value in doing a review because you have all the materials for the review. Everything I've given you, you need to know. And I apologize if it seems like a lot of material, but it's the structure of this course that it's intense that may seem overwhelming. It's during the week that you need to set aside time to review the materials I've given, because unless you have questions right now, I am going to refrain from talking about Unit 1 and Unit 2 GDS. I'm going to move on because our program indicates that today we are going to discuss the normal distribution. Okay? So please send me, let me know your questions. Actually, no one has asked me any questions by email, so I'll ask you to send me questions now or ask me questions. Some people are asking me for the link. I did send the link, and if you do not see the link in your email, you can just go to the same playlist, MBAUNDH playlist. Everything should be there. I'm just checking my email. If the video is blurry, please refresh the video because that's your end. Well, I don't know, it just does that. So if it's blurry, you need to just refresh your screen. How do you know what's the best class? A size? Well, in the problem I was just looking at, I addressed that issue. How do you know what's the best? Should you go by 5 or should you go by 10? It depends what you believe is the case. So you want a class size that reveals, so the steps, the objective of your class size is to reveal regularity and curiosity. Or any curiosities. Okay, so you want to see the general pattern of the data, but you also want to be able to see details and anything strange. So in this diagram, I see the regular pattern, and I see this curious, I see a gap here, and I see these surprisingly high expenditures. But the question becomes, the only difference between this class size and this class size are the 3 peaks. Otherwise, all the other features, the features of the center, the feature of the center, sorry, the spread, what am I saying? The shape. I'm going shape, center, spread. Well, the 3, actually I should correct that because it's the 3 are the same on this drawing. The shape is the same. You still see right skewed and right skewed. The center will be found in the same summary calculation because you're going to use the median. The spread will still be the 5-number summary. What will change are the gaps and outliers. So the difference between these two would be in the gaps and outliers and the peaks. And you have to decide, unfortunately, you have to make an executive decision of which drawing you prefer to make a summary statement that you consider appropriate. Okay, so in this class, I will tell you which class size to use. Okay, you won't have to struggle with that, but in reality, you should make all separate drawings and see the differences and make your decision. In particular here, I like the peaks are different, and I prefer this one. Okay, because of the story I can tell about low, middle, and high income earners. Okay, other questions? Did you meet with Taylor during the week? Or is Taylor going to help you next week? So Taylor, he has access to all the same resources, so you can ask him any questions. And I could also offer some time next week, and I have offered, if anybody wants to meet with me, I can arrange a Zoom meeting or a, I don't know, we can make, I do office hours. I've done office hours with my students, with a couple of students. I meet on YouTube and so answer their questions. So next week, of course, we're all busy, but I do not have classes during the week. I only have classes on the weekend. I have classes on Fridays and Saturday and in my campus, so on my campus. So you can ask me questions all week. So the question is there a standard range or class? Nope. You just go with the data. So the interval that you use will depend on the data. So you notice for Maris and Ruth, sorry, I'm going through the data here. So here, what did I do? What I did in the output, this is for Maris and Ruth. Before I put them together in a stem and leaf plot in the notes, in a back-to-back stem and leaf plot, I first did them separately. And notice Maris was by 10. But Ruth was by 5. Now obviously I had to use the same stem for the back-to-back stem and leaf plot, so I had to choose which one I wanted to use. And again, the rule is pick the one that best reveals the regularities, the pattern, the regular pattern, and any kind of curiosities. So as I mentioned, the only rule is that you pick the interval that tells your story. All right? So you can draw them in several ways, decide what the story is behind the data, and then choose that number of intervals. Okay, so this is your exploratory phase with the data. Oh no, so not everybody could meet with Taylor. Well, we're going to continue here, and all the videos are online. Just send your questions to me or Taylor and we can prepare them and post them so anybody can see them at any time from any place. How about that? So if you email me your questions, I can prepare the answers and put them on YouTube for your viewing. The Zoom meeting, I'm not sure. I'm getting conflicting messages about whether to use YouTube or Zoom. If I use Zoom, what I would do is open Zoom and then live stream the Zoom meeting. That would be what I would do, so I could have both. The issue remains that if you want to interact in Zoom, then you need to be in Zoom. Okay, and then later you can watch the video on YouTube where you can have the translation and the timestamps, etc. So that's what I can propose. But the structure of this class has already, the framework is already there, the materials are already there for you. You need to work through the materials. This is structured as a hybrid course. Unfortunately, we're not meeting in person, but we are meeting live stream. So for me, it's adequate. Okay, so but you have to come prepared to the live streams to ask me questions. Me solving problems is not the answer. You have me solving problems on maybe 20 hours of videos. More than that. Probably 100 hours of videos if you start digging, because they're all different playlists. All right. No questions? In this handout, so this is the GDS handout. So what we've done so far is looked at, together we've looked at Maris and Ruth, we looked at the spending data, there is also the Newcomb data. Should I continue? I don't know if Zoom automatically translates, but what I'm suggesting is I can live stream the Zoom meeting on YouTube. So we can meet in Zoom, and then I can have that on YouTube at the same time. So then YouTube will translate the discussion. I don't know how it will do it with 2 different languages, but I think I can set that up. I think I can set up 2 different language feeds. I think I've done that before. I've seen that before. I don't know that Zoom does it automatically. I was going to check that today, but I didn't check. Okay, I have a question from Luxo. Louis, what difference between stem and back-to-back stem? So the difference between stem and leaf and back-to-back was the drawings that we made. Did I do it here? Where did I do my drawing? Let me see where I put it. I think it's over. I think it's here. I don't know. One moment. Oh, I don't know where I put it. So we made a back-to-back stem and leaf last class. Maybe I deleted it. I don't see where it is. Did I put it here? Maybe it's on top. I can't seem to shrink this. Oh, here. There it is. Okay, let me get it here. So this was so this was the back-to-back. What we did was we used the same stem for both groups. That's back-to-back. All right? So watch the video from last class where I did that if you don't know what I did. But I used the same stem. So that way we could compare on back-to-back. I could see which one is which one has higher hits, and I see that the peak of Ruth is above almost the complete data set for Maris. And that's important because the expected value, the average or the expected value for Ruth exceeds all of Maris's data except for one, the one extreme one. More questions. So you should be coming prepared with your questions, all right? As I have hours of questions and solutions that you can go through. If I keep making them up, it's, again, redundant. So, no, that's not it. All right, so this is where you have the review problems, the exercises, all the videos. Okay? So work through these, and then these are in the Comunidad platform. And then try the quizzes so you get a better idea, and you can ask me if you have trouble with the quizzes. Somebody wrote me, someone did ask me about a quiz here in the DNS section, and it was about blocks, and I don't know which one it was. I'm not sure which question. So if you ask me a question, please let me know where it is, and I can look for it now. Guess. No, it wasn't this one. It's not the first one. Anyway, so if you ask me a question, tell me exactly where you're getting it from. It was a question about factors. I will have done all of them by the time this is over. Any other questions? So these are all problems you can try. Okay, so I think this was it. You are going to run a field experiment to investigate the effects of 4 fertilizers on the yield of wheat. You have 40 plots of land available and you wish to run a block design. And so then in the options, you have to pick the best answer. Remembering what blocks are, oh, sorry. So the point of blocks, remember, blocks receive all the treatments. That's the key to getting these kinds of questions right. Okay, blocks receive all treatments. And blocks are just groups that are systematically different, are blocked off so that they can receive all the treatments each, and we can have better, fuller information. So, so you guys should try all the quizzes and get back to me when you're stuck. Email me or Taylor, okay, with direct questions. I don't know what else to do, but you have to do the problems. I can't do the problems for you. The quizzes are not required, they're just for you, for practice. Okay? So I can't, it's already it's 6 o'clock, and we spent an hour, and I cannot spend more time on this. So what I will do is make a separate video answering any questions you have, okay? I will make a separate video, not in the hour of the class, because we need to move on. So if you want me to answer the quizzes in a separate video, I can do that for you, all right? So I'm going to list off what you've mentioned you want me to do. You want me to do quiz 1 point. Okay, 1.3 and 1.2 questions 2 and 3. Harry Charles, is it that you want me, or Charles, do you want me to do, oh, I see, 1.3, the quiz, and then 1.4, is that what you want? So you guys want me to do all the quizzes? Well, I guess I can do that, okay? So I'll make a video with all the answers to all the quizzes. It'll be a short one, I hope. Maybe an hour, less than an hour. All right, so I want to move on to the new unit unless you have more questions. So I will. So I'll post a video with the answers to the quizzes in Unit 1. And then you guys, if you have questions, you can comment in the video underneath and ask me questions, or you can email me. I mean, the interactive part comes from you, okay? There's opportunities to interact. We have email, there's a comment section, there's a chat here. There's plenty of opportunity to interact. In Zoom, we can interact. We'll see how that goes. We can try that tomorrow morning with the link. We can try to function in Zoom if you prefer, and I can broadcast on YouTube. So the link was already sent, and I just had trouble trying to set up myself as the host in the past, so I will try and do that for tomorrow morning. Any other questions? Okay, so I'm on Unit 3 now because that's what we are supposed to be discussing. Sorry, I wanted to do Newcomb's data and then we'll do Unit 3. I'm sorry, I'm jumping. Yeah, I wanted to discuss Newcomb's data and then we'll get into Unit 3. So that's the last thing I'm going to do from Unit 2. But Unit 3 is available. So, in the sample problems, we have Newcomb's data. And I mentioned last class that this is data on time, different from 24,000 and some nanoseconds that it takes light to travel over a certain distance, and this was the data that was used to estimate the speed of light. So here is the data in numerical order, and what I presented in this document was this stem and leaf plot for the data. And you see when you have a lot of data, the classes become redundant because there's so much data. Well, this is a very tight distribution. Many observations are here in this class, and just a few outside here. So this is a very regular pattern. For this data set, this part of the data set, and then just some outliers here. And so what do you think about that? Is it likely that there would be variations from a physical phenomenon like the speed of light or the time light takes to pass a certain distance? Should there be such variation? Is the question. So we see this. This is our drawing. I've drawn it here as a stem and leaf. And then below, it appears as what's called a histogram. That's not very neat and tidy, is it? Let's write it nicely. This is a histogram, and I'm going to discuss how to make a histogram. In particular, this is called a relative frequency histogram because it shows you the percent of observations in each class. This was generated from a computer, and you can set, by programming, you can set how you want the intervals, and you can set the starting point and the ending point of data depending on the software. I don't expect you to program in statistical output. I just wanted to show this graph. You could do this by hand manually, and we will do that in a moment. But first I want to discuss the regularity. And this is the curiosity. It's time to investigate these data points. Could it be that there is a data entry error? Now at this time, this was data collected 100 years or so ago, so they didn't use a keyboard or anything like that, but maybe transcribing from the notes to somewhere else created a data entry error. Could it be a measurement error? So in that case, maybe something happened in the field when the measure was taken. The instruments stopped working, or the researcher collecting the data was disrupted somehow or distracted, and made an error in measuring making the measurement of seeing the light in a mirror that he was observing for. Or maybe there is a paradigm shift. Maybe there is an imbalance of some sort in the speed, and it's worthy of further investigation. So which one of these will explain the obvious outliers? So we need to take some time to look at that. Was it a data entry error? Is it a measurement error? Or is there actually something special to report on, a paradigm shift? There's regularity, but occasionally there's glitches in the physical world. So it turns out in this data set, when we take the data and plot it this way, this is called a time plot, and the time plot has the order of measurement on this axis and the measurement here of the variable time on this axis. And what do we see when we look at this plot? What can we say? Most of the data is up here between 20 and 40. But there are a few observations out here. However, these observations happen early on. How do you conclude? Are you currently seeing the captions? Can you turn the captions on in the translation so it translates as I speak? Is that possible? Because I selected an option that allows, it should allow for real-time translation. The problem with the real-time translation is that you're trying to watch the video and it's hard to also watch the the translation. All right. No comments? All right, so these two observations here that occur earlier on, these are outliers, but I want to define them. Thank you, Kathy. Louis Charles. It should be showing up, but anyway, you guys can watch it. Hopefully, with time, you can watch this again and get the translation. I did not use R. I used a software called Stata. Not to get this one, to get this one. This graph here is just it comes from the textbook that I got this data. All right, so these are outliers, and I'm going to conclude these were measurement error. Because they occurred early on in the process of collecting the data, I believe that it was a result of the researcher making mistake in collecting the data and making the measurement. All right? He was getting used to the instrumentation, getting used to the environment, and he made mistakes early on. So my decision, since it's measurement error, I'm going to drop the observations. Alternatively, you could correct them if you have a way, but in our case we don't have a way of correcting. If the outlier, oh, I spelled outlier wrong. If the outlier was the result of a data entry error, you would do the same thing. Okay, you could either drop the observation or correct them if you have information to allow you to correct them. Okay. If there's actually a paradigm shift as a result of seeing outliers, you see a completely different behavior, you want to keep that data and analyze it. It's hard to get my pen steady. Let me try it again. All right. So in our case, we're going to drop the observations because we have no way to correct the observations. We're just going to drop them, and we're going to go from a data set of 66 observations to 64. Yes, there's gaps caused by the outliers here. So what we're going to do next, if you have any comments, you can put them in the chat. And what we're going to do is redraw this, and instead, when we drop the observations, the sample size becomes 64. And we get this lovely symmetric histogram. So I want to create this histogram with you. Although I do have a video with that. I need to emphasize it now to get on to what I do next. So let's take a 5-minute break so I can get organized. Let's take a break, and when we get back, we're going to make this histogram. Called a relative frequency histogram, okay? Again, if your screen is blurry, refresh the page. Okay, I'm back. I am back, and what we're going to do is make a relative frequency histogram for Newcomb's data. So here's the data that I cut and pasted from Newcomb. And because we decided that these two are outliers caused by measurement error, since we can't correct them, we're just going to drop them. We have enough data we think that's not going to affect, well, we believe that they're just real error. We have enough data that's stable, and we believe that this was just a mistake. Now, having said that, you shouldn't drop outliers unless you have a solid justification for doing so, okay? You might miss some important paradigm shift that you shouldn't ignore. So they could be telling you about the insecurity of your data set and something very important going on. So it's often discussed that this is really important in engineering, to make sure when you delete observations, you're not risking safety in doing so. Now in this data set, we have observations in the range of 16 all the way at the bottom to 40. So 16 to 40, the range of values what I think would be, so now I'm going to decide the class to use, and I want I can calculate the range as 40 minus 16. It's 24. So if I want to have about 5 or 6 groups, I'm going to need 4 or 5 as the interval or the class size. I want to move this over. Okay, that worked. All right, so I'm going to use classes or 5 classes, let's say. Okay, so this time I'm going to include from 15 to 20, that's my first class. And what I'm going to do is include 15 in that class and not include 20, because I'm going to start the next one with 20. So this firm bracket, square bracket, means include 15. This soft or round bracket means do not include 20 or exclude 20. That's what this hard bracket means and this soft bracket. And then we start with this one. This second class includes 20 but excludes 25. And I continue with 25, 30, 30, include 30 but exclude 35. The next one includes 35 but excludes 40. So all the values that fall in this interval, we'll count them. Let me just finish the classes and then we'll do that step. So then this one is 40, includes 40 up to 45. And is that enough? Yes, it is. So I ended up having 6 classes, 2, 3, 4, 5, 6, because I went back here and I need 40, okay? So this actually works out to be 6 classes, but anyway, roughly the case. So let's count now. Now what we're going to do is count how many observations fall from 15 to 20. So this is the first, second, and the third, but I don't include 20. So 1, 2, 3. Okay, so the question is, why didn't I use 19? Why did I use 20? So this is different than the stem and leaf plot because I'm treating in the stem and leaf plot that we made, I was treating the values as discrete, but here, because of continuous values, I'm making a histogram now, and that assumes you have continuous values. So it means that I could go up to 20, but not including, I could have 19.999, and that would fall in this class, but 20 would have to go in this class to avoid overlap, or to ensure the classes are mutually exclusive or distinct, unique. So I don't put 19 here because 19 is not implied in a histogram. It's actually 19.9999 and so on, and it's too complicated to write it. Anyway, that's the logic of what I'm doing right now. The fact is the data doesn't have any decimal values, I understand, but I'm trying to teach you the general approach to making a histogram. So this is what you do. Oops. I don't want to erase that. I just destroyed that. Jeez. There. So sensitive. Does that make sense? So if I was to write 19, I couldn't just write 19 there. I would have had to put 19.9999 and right? Because there might be decimal values in a histogram, the way that it's drawn. All right. I hope that explains it. So let's continue counting. So in this class, 20 to 25, we can count this as a group of 5, so this will go much faster. So this is 5. And then this one is 5, and we keep going until 25, but do not include 25. So there's 5, and then 10, 11, 12, 13. So up to here, that's 5, so that's 10 and 13. So I will note that there are 13 observations in that second class. Now from 25 to 30, let's do the same thing. Don't forget about these two here. So we have 5, another 5. This is the big one. 5. Oops. Keep going. Another 5. We're almost done. 5 and 1 here. All right, so what did we get? Let's count the 5s first and then add on the extras. So we have 2 here. So I have 5, 10, 15, 20, 5, 28. I count 28. Can you verify that for me? I count 28. And next, so I want to go up to 35, but not including 35. So that's 5. Okay, this is 4. So 5, 4. So 5 and 8 is another 13. Everyone agree? And then the last two are easy. I want to go between 35 and 40. So that's 6 and 1. All right, so let me give you a moment to finish. Let me know when you're done. Yeah, so the convention looks so. The convention is to use a square for including and a round for excluding. If you want to do it another way, just tell me your rule so I understand what you're doing. But I'll be able to see as long as it's distinct. I'm not sure. Oh, interesting. I see what you're saying. A backwards bracket. But I've never seen that before. But yeah, that would make sense. If you did that, I'd be fine. I'd understand what you're trying to do. I've never seen that before, but maybe you have seen that open bracket. Thank you for to point that out. So if someone does 15, oh, I can't put it there. I need that. Well, 15, 20 like that. I get it, but that's not really the convention. But I'll accept that if that works for you. You just need to be able to read other people's work. It's usually like this. All right. The rest of you complete the chart. Oh, you cannot see the bottom? There. One more. The last observation is 40. So I should specify, I'm just trying to figure out a way, using the range here, you can come up with an idea. If you want five groups, or sorry, 5 or 6 groups, they would have to be of length 5 or interval 5. So you would use the range to figure that out. Okay. So let's make a drawing. Oh dear. I'm going to do this on another page. So what we have is right? Not sure why it's going so slowly. Okay, there you go. All right, so let's draw this. I'm going to put at the top relative frequency histogram. Newcomb's data. So you have a title. And then I'll try and make this straight line. And we are going to go by 5. I could start at 0. But then that just extends things, doesn't it? Move that over a bit. There you go. So I would, I can put the axis here and call this time, because that's the variable. The time is the variable, right? And on this axis, I put the frequency, or the number of observations. This stands for observations. And trying to make these lines as straight as possible. And if you look here, I have to only go about 30, right? Because this is 28. So I need to go between 0 and 28, or 30, sorry. So I can also go by groups of 5. So I can mark 5, 10, 15, 20, 25, 30. There you go. And this is just a sketch to demonstrate this to you. And what's most important is that you understand the interpretation. If you want to produce this in statistical software, if you want to use Excel to produce this, you can just watch a YouTube video and figure it out. So I recommend you to do that. But what's really important right now is that you understand what it is, where it comes from. Okay, that's my objective right now. So in the first class, beginning over here, 15 to 20, I have 3 observations. So I'm going to mark with a bar about 3. And I'll put the number 3 in here so that we can agree that that's 3. And it's not perfect, it's just a sketch, but we can agree. So let's say 13 is about here. And I'm going to make the next bar. Okay, now this bar is going to be thicker because my intervals are uneven. It shouldn't be. I'll make them a little more even. Okay, so that's 13. And the next one, 25 to 30, has 28. So I have to go all the way up here for this one. and it's sloppy, but it's just a sketch. I'll try and improve it. I do have a video on this that you can watch. Maybe it's better done neater because it's edited. But there you go, 28. The next one is 13. Then 6. And the last one, I'll move this over a bit. Is 1. There you go. This is called the relative, this is not the relative frequency, sorry, this is the frequency histogram. I have to check. That is the frequency histogram, so let me change that. And we're going to do the relative frequency histogram next. So this is called the frequency histogram. Okay, because I have on this axis the number of observations. And that's, so it's frequency. We call that the frequency. So what you can see in this graph, remember we can, from this graph we see a shape. What shape is this graph? This graph is clearly symmetric. Okay, it's symmetric. You have most of the observations in the middle, you have a few below, and just as many above. And you have less further from the modal class, and you have a little bit more here, but we'll still say this is symmetric. This is roughly symmetric. Well, it's symmetric. With more data, I believe, if we had all of the data possible, that this would be a smooth, histogram. Hit the microphone. So I think that this will give it a symmetric density. So remember, this curve is the idealized version if I had more or all data possible. I think that would be the pattern. Okay? I believe this is the pattern. I don't know what just happened. All right. So that's a frequency histogram. What is a relative frequency histogram? Nope. So what I'm going to do, I want to move this over. So what's a relative frequency histogram? This is a frequency histogram with the number of observations here. If instead I compute the percentage of observations, I could repeat the steps and make a relative frequency histogram. Let's try that. Any questions so far? Okay, so some people comment that they think this is skewed. This is not skewed. There's just a few extra observations over here. To call something skewed, remember you need those, we had those gaps, we saw those gaps, right? Gaps would indicate that you have extreme values. But there's no gaps. This is quite tight actually. Look how tight it is here. And then there's 3 observations and 7 here. Out of 64, that's not a lot. You only have a few extra on this side. Otherwise it's balanced in the middle. So this is symmetric. Remember, data isn't perfect, but if you had more data, you would see the clear pattern. I make an executive statement or executive decision that this is symmetric because I believe if I had more data, it would even out. I would get some more on this side and it would be even. Not perfect, but slightly. So there's no gaps. That's the important thing. Okay, so 3 out of 64 extra is not enough to call this skewed. Not in my book. Mostly because there's no gaps. Okay, if there was a gap and then you saw 3 out of 64 far away, that would be different. It's not, I'm not saying it's perfectly symmetric. But it's symmetric. You can say if you want, if you're not comfortable, roughly symmetric. It's not perfect, but it's more symmetric than it is skewed. Okay? So skewed would need a gap or very few observations and this very separate. So I provide instruction in the notes and the videos on when on the box plot, using the box plot and the 5-number summary to determine if you have skewed distribution. And I recommend you watch that video. That would be, let me confirm which video that is. So if you watch V4, and V5, I explain how to use a 5-number summary to determine if you have skewed distribution. Okay, but this is not skewed. Okay, so now percentage of observations. This is where we left off. You can keep writing your questions in the chat and I'll get to them. So percentage of observations, if n is equal to 64, then 3 out of 64 is what percent? That's how you compute percentage. So this turns out to be 0.05. Well, let's be precise for a second. 0.04 0.6875 or 0.05. So I'll just say that's 5%. Okay, so that's 5%. That's how I'll do my calculations. So 3 out of 64 is 5%. 13 out of 64 is 20%. So I'm just going to round to whole numbers. That's 20%. And 28 out of 64 is 44%. And 13 out of 64 we know is 20%. And 6 out of 64 is 9%. And finally, 1 out of 64 is 2%. Now, let me move this here. And show you that if we did this right, this should all make how much? Am I off a bit? This is 5. $20. 44. What we can do I think it works out. So you add them together. And you have a 100%, which will always be the case for a relative frequency histogram. The number of observations sum to the total n equals 64. So the graph that's made with this column will always vary from histogram to histogram. But relative frequency histograms will always have the same percentage of bars, 100%. So you guys asked me the question, when can you use a histogram? You should use a histogram when you have a lot of data, more than 50 observations, okay? So in our case, we had this data from Newcomb, and you see there's lots of data here. So that's why we did that histogram. We could have made a histogram for the spending data as well. There was a lot of data there. It was just 50. So that was a borderline case in the spending data, right? In the spending data, there were 50 observations, but Newcomb has 64. So that's when, when you have continuous values, you make a histogram. When you have more than 50 observations, make a histogram. All right, so Let's make what we're calling the relative frequency histogram now with this new column. And I will reproduce it. Let me clean it up so you can see the numbers clearly. So this one will be 5%. Five percent, 20%, 44, 29, and 2. So the question is now, let me check your questions first. Ironel, I'm not sure your question. I'm not understanding the question. Maybe you can rephrase it. So let's make a histogram with these percentages instead. Wait. And I have the question for you. I have a question. Oops. Do you think that a histogram produced with these values for the percentages will look different than this one? That's my question. So let's see. I'll do the same thing. I'm going to move this over and then I'm going to move this over. I think I'm going to move this over. All right, I'll just make it down here. So we do the same thing. It's the same timeline on the bottom. Not timeline, but sorry, the time variable. This is time. And now this is a relative frequency histogram. And Now we're going to put percent of observations. Okay, or let me write it simply, percent of observations here. Now the values this time run between 2% and the highest is 44. So I will make a chart. Actually, I should move this down. Okay, so we're going to chart, I'm going to chart 5, 10, 15, 20, 25, 30. Nope, it's not enough. I have to go even further down. Okay. So 5, 10, 15, 20, 25, 30, 35, 40, 44. So you should get the point of what I'm doing. You should be doing this, in fact. It's not worthwhile for me to do it. I have videos of me making this. That's not going to help you unless you do it. Or maybe you're following. But I think it's important to enact what you're doing, to put it to memory. So the first group is 5%, and it begins in the class 15 and 20. I need to move these classes over. I'm going to move this over, right? So for 15 to 20, it was 5%. So I'm going to put this I need to move this up. There you go. So 15 to 20 is 5%, so that would be here. And then 20% would be 20 to 25, so that's 5, 10, 15, this is 20 here. And then 44% would be all the way up there. 20, 25, 30, 35, 40. So it would be all the way up there. It would be 45 or 44. Remember, I just want the broader pattern. And then 20% again, and then 9%, and then 2%. So this is the relative frequency histogram. You can include the percentages inside. You could write them in here if you wanted. Okay, I'm not going to do it. And now I ask you the question. I've made the relative frequency histogram and the frequency histogram, and tell me now, do the histograms vary in terms of the 5 features? of a distribution? That's the question you want to answer. Do they vary in terms of the 5 features of the distribution? Well, the shape is the same. You guys are still going to argue, some of you, that it's skewed, but I would say it's symmetric, because I believe that if I had more data, that this would fill in over here. Okay, so this is symmetric. They're both symmetric. The center is in the same place. The center would be this here, between 25 and 30, and it's the same over here, right? Doesn't change. The shape, the spread would be measured the same way. You would use, in this case, since we're saying it's symmetric, you would calculate a mean for center and a standard deviation for the spread. 4, there are no gaps, no outliers, nothing set apart from the greater data set, and there's a single peak. So these frequency and relative frequency are essentially the same. The only difference is this scale here, which I could modify so that it looks exactly like this one, just use a different increment. Here I use roughly the same increment length for 5 and 5, but I could use a different visual scale here. And I can make these look the same, identical. So there's no difference between the appearance in terms of the 5 features of a distribution of the frequency and the relative frequency histogram. So why do we choose to use, in statistics, we choose to use the relative frequency histogram more often? That's not very clear, is it? It's hard to write with a pen. So that's my next question. Let me check your comments. Okay, more accurate. Not exactly because more accurate. Let's remember what's under this graph is always 100% from relative frequency histogram to a different relative frequency histogram. There'll always be 100% of the bars here. So what that allows is for me it facilitates, I mean, you can be more precise in saying 44% of the observations lie in the modal class. So almost half of the observations lie in the modal class. That's a lot of information. Then what is here? It says just 28. And here it says 28. And then you'd have to, there would have to be a second question. 28, how much is 28 out of 64? It's easily available in the relative frequency histogram. 44% implies a lot. So the reason why is because the ease of interpretation. It's easy to interpret the area, the frequency underneath. Okay? And it's also easy to compare between histograms. So the lesson is that the frequency and relative frequency have the same 5 features. However, the convention to use a relative frequency histogram is due to the ease of interpretation and for comparing between relative frequency histograms, because they will all have the same bars underneath and interpretation underneath. The same total percentage underneath, okay? So that is from there, unless you have some questions, I want to move into the normal distribution with the remaining portion of the class, okay? We're going to begin with the relative frequency histogram. Yes, Kenold, you have a clear comparison between all the observations. Yeah, so relative measures, statistics is about, let me make a thing. Statistics, actually, you know what, I'm going to put a box. Okay, so statistics is all about, oh, I want to make that bigger. Statistics is about expected values and relative measures. So far, I've shown you how to compute the center of a distribution and determine what to expect. And then we talk about relating other values to that measure, the expected value. And now you learn about histograms, where the relative frequency histogram is more meaningful because it shows you the distribution and the relative distribution of the values. and how the values, the observations, compare to one another. So you're more likely, and how much more likely here, to expect the expected value or the center? 44%. That's more meaningful than telling somebody 28. They could take 28, divide by 64, and get 44%, but it's more easily, immediately available from the relative frequency histogram. And yes, your answer is correct, Kenold. All right. So with that, I'm going to move into the normal distribution discussion and then leave you to review. Well, I don't know if you're going to have any time tonight, but you can try and catch up to where we are before tomorrow's class. Again, in the I'm going to show you in Comunidad So really, you have to watch enough videos every day to keep up. But I have all these videos for almost every page of the normal distribution. All right. I also have the lecture notes that we're going to discuss. Most of the solutions are, all the solutions are available watching the videos, and I'll do as much as I can today and tomorrow before we move into the last unit. So this is the second part of Unit 2, normal distribution. So this is called Unit 2 NOR. There's all these videos that cover all the topics for your review, practice assignments for you to review, and more quizzes. The last day we're going to do regression. So we're going to spend most of the time on the normal distribution today and at least half of tomorrow. All right. So you'll see most of the pages are covered. Page 2 and 3, 3, 4, 5, 6. I skip a couple of pages here and I can discuss those, and then all the pages are covered. So this is a complete review of the notes, except for the first few pages. So that's what I want to discuss now. I mentioned throughout the notes this link. This link will take you to the playlist with all those videos in it, so you can watch them in succession. You don't necessarily have to be on the Unidad Comunidad platform. All right, so we're going to talk about normal distribution. All that you learned so far, you learned about collecting data, the different kinds of variables. I told you we will focus on quantitative data. And then we talked about symmetric and skewed distributions. And now I want to focus on symmetric distributions. Approaching the concept of normal distributions. So some of you may have learned normal distributions in the past, and that's fine. So I just want to introduce the topic, beginning with density curves and then symmetric distributions. So recall the relative frequency histogram. We can think of a density curve as a smooth, idealized version of a relative frequency histogram for a symmetric distribution. So here it is. Here is my histogram. You know where it comes from. You understand the classes that are created and the data inside of here, that the classes are of equal length, and that the height of the bar represents the percentage of the distribution. For a symmetric distribution, the modal class is in the middle, here. So I can smooth out this distribution. Like that. It's not great, but and you can smooth it out, and then you can say that the total under the curve, the total bars under the curve will always be 100% for every relative frequency Okay, so under the curve will always be 100% for all relative frequency histograms. So because this curve implies that I have all of the data, this says, if we had all the data, we believe this will be the shape, okay? That it'll be symmetric and smooth. But having all the data implies that we have the population. So if we see this as the population, then in the population, the center for a symmetric distribution is the mean. And in particular, this would be the population mean. So the symbol for population is this Greek letter that I mentioned to you, the Greek letter for M, or mu. So M for mean. Okay. And then we are going to use the symbol X to represent a random variable, so a variable that is not the same number, that takes on various a variety of values and has a random process. And we're going to use the lowercase value x, the symbol x, to represent a specific value. And here I'm not being in general, this can go from the low values to the high values. So this is low to high. This is the number line, okay? And what I say is, so I'm going to focus on this, and I'm going to say let's call this value right here little x. That's the idea. But let's put a number on it even. Let's just say this is 64. So I could say little x equals 64. All right? Now, let the symbol P, I'm going to put it up here. We're going to use the symbol P to represent proportion. So it's going to represent proportion or percent. And so what I'm going to use it to talk about is I'm going to write that since this marks half of the data on the left and half on the right, it's the mean, it's the balancing point of the distribution. I'm going to refer to this P, and I'm going to use the symbol. Now I'm going to write this in statistical notation. Oops. What just happened? What just happened? Sorry, I touched something. So I'm going to write X in the middle. So that represents the curve. So X, we'll interpret X as when we see X, we're going to say actually, let me not write that right now. Let me just talk about it first, and then I'll write it. So we're going to say the proportion of observations under the curve that are less than 64, what percentage or what proportion of the values of X are less than 64? Do you know the answer to that? I made up the number 64. Okay, I introduced the number 64 just to put a number on it. I'll show you with the variable later. Okay, so I just called it 64. It turns out that 64 is the average height of women that's going to be used as a ongoing example. It's 64 inches is the average height of women 18 and over. So from this, with this drawing, and I'm telling you this is in the middle, this is the mean, and this is a symmetric density curve, what percentage of this, what percentage of the area under the curve is less than 64? Just look at it and comment. I'm trying to formalize the notation, and I took the easiest one I could think of. So what percentage of the area of under the curve, so these bars, what percentage is less than 64? No, just example. It's just an example. The rule is mu. That's the rule. I just put a number on it because it'll look too, it might look too confusing if I just put symbols everywhere. Yes. So people see it's 50%. Very good. So this is, because of the one that I chose, it's 50%. So I could also write that as right? So for a symmetric distribution, the proportion of observations of x less than the mean is 50%. I'm going to, so I'm going to tell you there's, so this is, I'm going to use P to represent proportion, percentage. Now there's two more ways. I could also call it frequency. P represents frequency, right? Or relative frequency. Let's write it like that. Right? Or some people can say frequency too, but it's really relative frequency. And there's one more interpretation of P. P, since this is the entire population, the chance of being less than 64 or less than the mean on a symmetric distribution, we also refer to as the probability. So P is all of those things. Proportion, percentage, relative frequency, and probability. Okay, so I use P, or sometimes I write, you might see the symbol PR. Sometimes I write PR, okay? All right, so let me ask you a few more questions. I'm going to erase this one because this looks a little bit confusing probably. I'm going to write it. So some of you like numbers, some don't like numbers. So what I'm going to use is symbols. So what I'm going to say, let me make this a little larger. So take a screenshot. I'm going to make this larger right now. If you're trying to copy, just take a screenshot. All right, so making this bigger. So if I'm here and I'm going to use the symbol x1 and say this is 10%, then we can write probability that big X, the variable X or the area under the curve, is less than x1 is 10%. You can write it like this. You can write it like this. All right? So if I give you this, you can write this. So what do we call x1? Does anybody know? What do we call 64? So those two questions. What do we call x1? What do we call 64? Has a special name. Jean, the portion is 50% because it's half. Half is 50%. Okay, so the question was, what do we call x1? x1, well, let me do this one first. And I said, what do we call 64? 64 is called the mean, but because the distribution is symmetric, 64 turns out to be also, it is the mean, it is the median, and the median is also the 50th percentile. It is the observation where 50% of the other observations are below it. So it's the position where 50% of the other observations are lower. So 64 is the mean, it's the median, and it's the 50th percentile. So with that information, can you tell me what x1 is called? x1, come on, someone tell me. Okay, it's not the chord of the mean, but it's the what? If 64 is the 50th percentile, x1 is the what percentile? So Q1 is the 25th percentile. What is x1? It's called the 10th percentile. Okay? Let's see, where should the first quartile be? The first quartile is where there are 25% of the observations below. So let's see, I can put that, let's say that's here. So I'm just trying to teach you the symbols. So let's say the way I'm drawing this, if x2 is the first quartile, then we would write, I'm trying to think of where to write it. So x less than x2 would be 25%. So 25% is a quarter of 100. So that's what makes x2 the 25th percentile. Now I'm just picking points, but I should draw it in. Let me clear this so I can draw it. So let's say it's the case that this marks 25%. So all the bars to the left of x2, or the area under the curve, notice we're not talking about this, but I'll explain that in a moment. All these bars here sum to 25%. Therefore, x2 is the 25th percentile. Exactly, Jeffson. 25% on the left and 75% on the right for x2. Okay, now let's look on the right. It's not so messy. So what if it turns out I tell you, oh, let's see. These, actually that's not true. This looks more like 7%. Okay. So let's say these under here sum to 7%. What do we call x3? What should we call x3? Good. Good idea. Good, good, good. So x3 is the 93rd percentile. What's another way to express that? We can write it like this. X less than x3 is equal to, you can write it like that in statistic mode. Statistic notation. Or you could say you can refer to the top, the upper end, and you can say x3 is the top 7th percentile. Okay, so if you refer to the right side, you'd have to express it as the top. Oh, you can't see what I wrote. It's in there, it marks the top 7th percentile. But it's also the 93rd percentile. So there's 3 ways to write that. So people who are confused, it's 93 because it's 93 on the left or 7 on the right. All right. Notice, oh, I can also write that in symbols. This is not going to leave me room, is it? So I could write that here. I could write the area under the curve is greater than x3 equals 7%. Okay, so I changed the direction because this arrow changed direction. So these arrows are aligned. Now notice I'm always using an arrow, like a sign like this. I am not putting an equal sign in here. Remember, we're focusing on, with histograms, we focus on continuous data, which is very important. I could write actually, let's do it like this. I could ask you about finding the area between x3 and x2. I could write that as well. How do we write that? You want to try that? I'm not going to ask you for the answer. I haven't given you the answer. I haven't provided enough information. Or have I? Well, actually, maybe I have. Yes, I did. Can you figure out the area in between, I've never done this before, x2 and x3? I guess you could. So let me ask you that. I'm going to write it as a, in statistics. Let me make some room. Let me erase. So my question is, what is the proportion between x2? Notice I have to write my symbols small to big. Can you figure out what the proportion of observations between x2 and x3 are? It's 25% over here, and it's 7% over here. The total is 100. What remains? So everybody got that? You guys are off. To figure this out, you have to take 100. Remember, this is just a density curve. This is a symmetric density curve. It's not a normal distribution. So I need to take 100 minus 25 minus 7, and in between we can even do 93 minus 25. That will give us the answer, right? So you can do it this way or that way. Oh, you did get the same. 93. Yeah. So either way, this is 68%. And that's a coincidence. I didn't intend it to be 68. But okay, so it's 68. And what we did to calculate that, the easiest way was we took the big value, the larger value, minus the smaller value. And what I cared about was the area under the curve, not the value x2 and x3. I just want the area. So that's 68. So that's the proportion of the percentage, or because we see this as the population, it is the likelihood or the probability. Okay, so we can do all of that. Everybody's good? But percentile is just defined as the area to the left. Very good. We're almost done here. So what we have here is a symmetric distribution. We understand percentiles, we understand the area under the curve, and what I want to do next, oh, one more thing before you go, and then tomorrow we're going to start with the normal distribution. Although we have talked about area under the curve to the left, to the right, and between, there is no density at a single value when you have a continuous distribution. We do not compute any density at a single value, okay? This is because the chance of being at a single point is, you can say, so unlikely, we'll say the likelihood or the probability or the chance is 0. So whenever you have the area under the density curve of any one particular value will be 0. So for example, the probability that the area under the curve at a certain point it will be 0. Also, it will always be 0, okay? So that is for a variable that is continuous. Not discrete. So we're focusing for the next few classes on distributions that are continuous and symmetric. Continuous variables with symmetric distributions. I've also discussed the concept of the pth percentile. It's the value that p% of the area under the density curve lies to the left of it, okay? And that I have a drawing below, but we've already discussed it up here. Okay, so I'm going to stop now because it's time, right? So tomorrow, have a good rest. See if you can review a little bit tonight. What I'm going to do is begin with the discussion of the normal distribution, because we haven't started that yet. We've just talked about a symmetric density curve. And see how much we can get through. Okay? Tomorrow I'll start in Zoom. Let's see how that goes. I really don't want to waste time with new technology, but I will do my best to set that up. If I have trouble, I'll send you an invite or I'll send you a link to YouTube. So stay tuned for my message tomorrow. We'll see you in the morning. Good night. I'll stay on if you have any questions right now. Is 9 a.m. okay? You prefer 10? I'm not sure where the 10 came from. Did I say 10? I meant 9. It's 10 a.m. for me because I'm an hour ahead of you. But it should be 9 a.m. Thank you, everyone. I'll stay back if you have some questions. Thank you, Kenol. Bonsoir. Thank you, Kenol. I'm glad you enjoyed it. I know some students are frustrated with the language, and I apologize. My French is only for ordering dinner and small talk, not for instruction of this sophistication. Thank you, Patrick. Thank you. Good night. You're so kind. Thank you, Jean. Bye-bye, Anouk. Bye, everyone.